All right. Thanks for tuning into this. As I mentioned in class, we're going to cover just a little bit more so that you're able to try out the questions on worksheet 3.2. So let's catch back up to where we left off in class. We were talking about how do we describe where electrons are in an atom because we know that the Bohr model only really applies to hydrogen. We're going over the address for the electron. The address is composed of the principal quantum number, the angular quantum number, the magnetic quantum number, and the spin quantum number. Your principal quantum number, which we call n, just tells us how far the electron is from the nucleus. Level 1, or n equals 1, is the ground state, or the closest to the nucleus, and then as we move to higher whole numbers, we're further from the nucleus. There's a formula to determine how many electrons can be at any given energy level, or how many electrons can be that distance from the nucleus, and that is 2n squared. So if we're on energy level 1, 1 squared is 1, times 2 is 2. So 2 electrons can be at level 1. If we're on level 2, 2 squared is 4, times 2 is 8. 8 electrons can be at the second energy level. The angular quantum number, also called the sublevel, more commonly, is what three-dimensional path is that electron taking, or where is the probable space that we can find this electron. And so we have 4 sublevels. They are the S sublevel, which I remember as the sphere. So here's this three-dimensional sphere, and anywhere in here is where you could find an electron that's in the S sublevel. You have the P sublevel, which I call the peanut. And so that's your three-dimensional probable space where that electron can be. The D sublevel, or I remember it kind of looks like the peanut, but 2 of them, so I call it the double peanut. D for d orbital, or d sublevel. And so that's the probable location we can find an electron there. And the F sublevel, or I remember what looks like flower. And so these are the three-dimensional locations where an electron might be at any given time. Remember, we can't know where the electron is for sure, but we know where we tend to find it anytime we look for it. Just like when you graphed your dropping of the dart, we know where those drops tended to hit. And so this kind of shows us where do we find electrons whenever we check for them. This gives us that probable location. All right, so let's keep specifying our address for our electron. After the sublevel, we then have the magnetic quantum number, or what we call orbitals. I like to remember an orbital as being like a shoebox. So a shoebox fits 2 pairs of shoes. An orbital holds up to 2 electrons, just like a shoebox holds 2 shoes. So for each sublevel, there's a certain number of different orbitals that we can have. And each orbital is holding 2 electrons. So let's look at these orbitals. For the S sublevel, there's only 1 orbital. It's a sphere. So we can't really modify that in any way. So 2 electrons can sit in the orbital of the S sublevel. For the P sublevel, there are 3 orbitals. We can think of them as the one along the x-axis, the one along the z-axis, and the one along the y-axis. 2 electrons can fit in each of these. So the P sublevel, if all 3 orbitals are occupied, can hold 6 electrons. In the D sublevel, there are 5 orbitals. Again, variations off of that x, y, and z planes of orientation. Each of those can hold 2 electrons. And for the F sublevel, there are 7 orbitals, each of them able to hold 2 electrons. So the D sublevel in total could be filled with 10 electrons, and the F sublevel in total could be filled with 14 electrons. Let's look at each of those in more detail. So here's the S sublevel. We can have 2 electrons traveling in it at any given time. The P sublevel, X, Y, and Z orientation, 2 electrons in each one. And so that gives us a total of up to 6 electrons. The d orbitals in the d sublevel, again, 2 per, so that's up to 10 electrons. And the orbitals in the f sublevel, there are 7 of them, again, each holding 2, up to 14 electrons. So our goal is to always get a better understanding of where every electron is. And so this tells us what sort of path they're traveling in and how many there are to full. If you think back to the POGL we did with the bunk beds, each orbital, like a shoebox or like a bunk bed, is full once it has 2. Our last number in our effort to describe where every single electron is in an element is the spin quantum number, or S. This tells us the direction that the electron is spinning around its own axis. We can have up to 2 electrons in an orbital. They must have opposite spins. We describe that as +1/2 or -1/2, or in other words, one spinning clockwise and the other spinning counterclockwise. You might remember noticing in our POGL that you were shown an up arrow and a down arrow for your electrons, and the up and down is meant to show that those 2 arrows have opposite spins. If 2 electrons are going to be in the same orbital, they cannot have the same spin. Just like in your desk, if 2 of you are going to be sitting at the same table, you can't be in the same seat. You have to be in different seats. Or if there are going to be 2 people in a bunk bed, they can't be in the same bed. One has to be in the top bunk, the other has to be in the bottom bunk. So for electrons to be in the same orbital, they must have opposite spins. So let's summarize. Our principal quantum number is how far they are from the nucleus, and it's given a whole number, 1, 2, 3, 4. The bigger the number, the further we are from the nucleus. Our sublevels are the shape of the path that that electron is taking. We have 4 variations, S, P, B, and F. The magnetic quantum number is the orbital. That's the number of spaces we have on that sublevel to hold an electron, every orbital holding 2. So in S, we have 1, P has 3, D has 5, and F has 7. Every orbital holds 2 electrons with opposite spins. So the S sublevel holds 2. If we're on the second energy level with S and P, we can hold up to 8, 2 for S and 3 for P. If we're on the third energy level, we have S, P, and D, S holding 2, P holding 6, D holding 10, 18 electrons. When we get to the fourth energy level, we have all 4. We have S, P, D, and F, 2 electrons on S, 6 electrons for P, 10 electrons for D, and 14 electrons for F, or a total of 32 electrons could be found on the fourth energy level. So let's practice with this information. What I recommend is that you pause the video now and try these out, and then check your answer in a moment. All right, so what is the maximum number of electrons that can fit into the third energy level? Well, our formula is 2n squared. So 2 times 3 squared is equal to 3 squared is 9 times 2, 18 electrons can fit on the third energy level. How many electrons can fit on the fourth energy level? That would be 2 times 4 squared. 4 squared is 16. 16 times 2 is 32 electrons that can fit on the fourth energy level. So, last question, can 3 electrons fit on the first energy level? Our answer is no. How do we know? First, we can check 2 times 1 squared equals 2. Also, we can think about on the first energy level, we have just the s sublevel, which has 1 orbital, and an orbital can hold 2 electrons. So there's no way to fit a third electron into the s sublevel on the first principal energy level. For the rest of today, what we're going to talk about is how do we diagram and describe where all the electrons are for a given element. And so first we can use what's called an orbital diagram. So pictured here on the right is an orbital diagram. It shows increasing energy. And so the higher up these spaces, the higher in energy they are. Let's talk about what these are. We have our large number, which is the energy level. And then you have your sublevel, the letter, and then a line represents an orbital. So if I'm looking at 2p with 3 lines, what that's telling me is second energy level, the p sublevel. The p sublevel has 3 orbitals, so I have 3 lines. Every orbital can hold 2 electrons, so I could draw 2 electrons there. The 2p sublevel is higher in energy than the 2s sublevel, which is why it's drawn slightly above it. And so we can see 1s, first energy level, is the lowest in energy, followed by 2s, then 2p, then 3s, then 3p. Then here's something interesting. 4s is lower in energy than 3d. So electrons are going to go there first. The way I like to remember it is think about in a movie theater. You have the main seats in the center, and then sometimes you have seats off to the side. If you were going to sit for a movie and you had an option, you can sit in the 3rd row off to the side, or you could move a row back, the 4th row, but you get to be in the center. Which is the better seat for viewing the movie? The 4th row center, even though 3rd row is technically closer to the screen, you're off to the side. So in that same way, the 4s is a better energy position for an electron than 3d. So electrons would prefer to be at the 4s. So how do we make these diagrams? Your electrons are going to start lowest energy first. So they're going to try and be as close to the nucleus as possible. When an orbital is full, then they're going to move on to the next available orbital. If all orbitals are filled, then the electrons will double up until there's 2 electrons in every orbital. When that's full, then they're going to move up to the next energy position. And we're going to use arrows to represent this. So let's go ahead and try an example. Let's make an orbital diagram for nitrogen. Now, nitrogen's atomic number on the periodic table is 7. That means it has 7 electrons. So we're still assuming that it's neutral. So we're going to start from the bottom, and we're going to work our way up. So 1s, I'm going to put my first of 7 electrons, and then I'm going to move on to any other orbitals. There are no other orbitals at this level, so now I'm going to double up, 2 electrons. This orbital is full, and there are no other orbitals, so I'm going to move up an energy level to the second, 1 electron. And then I'm going to move on to any additional orbitals at this level. There are no others, so I'm going to double up. I've now drawn 4 out of my 7 electrons. I've got 3 left. Now I'm going to move up again to the next available position. That's 2p. I'm going to put an electron. That's my 5th electron. There are more orbitals available. 6, 7. So notice, before we double up the orbitals, the electrons are going to fill out into each available orbital before we double up. The convention is to put an up spin arrow before you put a down spin arrow, but that's just convention. What's really important is we fill from the bottom up, lowest energy first. If there's available additional orbitals, we fill those before we double up. When that whole level is full, we move up to the next available location. Along with orbital diagrams, we can make what are called electron configurations. These show where the electrons are without drawing the large diagram that we just saw on the previous slide. Think of this like the manager's code you saw in our POGL. What are the rules for this? They have names based on who discovered them. We have the Aufbau principle, Hund's rule, and the Pauli exclusion principle. What do those mean? Well, Aufbau is a German word. Auf means out, and Bau means building. And so the Aufbau principle means to build out, or in other words, electrons are going to go from the lowest energy to the highest. So they're always going to start as low as possible and build out. Hund's rule, the electrons are going to spread out before they double up. And the Pauli exclusion principle, you're always going to have electrons of opposite spins. So you're never going to have two electrons pointing the same direction. They'll have opposite spins. So here is our, what we call our filling rule or our filling order. And that is all of our available places for an electron in the order that they will fill. So an electron is going to go to the first energy level, S sublevel, 2 can fit in the orbital. If that's full, then we're going to go to the second energy level, S sublevel, 2 can fit there. After that's full, second energy level, P sublevel, up to 6 electrons can go in those orbitals. After 2p6, then 3s, 2 can fit there, then 3p, 6 can fit there, then 4s, 2 can fit there, 3d, 10 can fit there, 4p, 6 can fit there, and it keeps going. So this is the order that our electrons will fill. So how do we write these? We want to write the electron configuration for one electron in the second level S sublevel. How would we show just that? Well, we're going to start with the energy level, 2. What sublevel? S. How many electrons? 1. I recommend you pause it here and try number 2 and then check back in for the answer. All right, the electron configuration for 3 electrons in the 4th level, P sublevel. So we're going to start with what energy level? 4. What sublevel? P. How many electrons are there? 3. Now let's try writing electron configurations for the entire atom, including all of its electrons. So what we need to do for this is we need to know the atomic number. Calcium is atomic number 20 on the periodic table, so that's 20 electrons. And so where are those 20 electrons going to be? Well, we're going to start in order. I'm going to reference either something like this, or I can reference my filling order here to know what I'm going to fill and how many it can hold. So while referencing one of those, calcium has 20. First energy level, S, holds 2. Second energy level, S, holds 2. Second energy level, P sublevel, holds 6. That's 2, 4. I've drawn 10 out of my 20 electrons, so I'm going to keep going. 3s holds 2. Now I'm at 12. 3p holds 6. That's 18. 4s holds 2. This is what we call the electron configuration of calcium. It tells us where all 20 of calcium's electrons are. Go ahead and pause the video now. And I would like you to try the configuration for bromine and iodine. When you're ready, let's check your answer. Bromine has 35 electrons. Filling in order based on our filling rules, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p. Now let's count 2, 4, 6, 10, 12, 18, 20, 30. That's 30 out of my 35 electrons. P can hold 6, but I don't have 6 electrons left. I have 5. So 5 electrons will fill into the P sublevel on the 4th energy level. Iodine has, I need to count, iodine has 36, 37, 38, 48, 53 electrons. So we're going to go again in filling orders. Remember, I'm referencing that filling order document. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p5. I can double check. 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 53. These are where iodine's 53 electrons are. Okay, that's it for your notes. That should get you to a good place where you can now go ahead and practice some more questions on your worksheet 3.2. Thanks for tuning in.